Hey, welcome back.
So now you know how the auto
Today's
transformer
presentation
operates.
is on electrical
Here
power
is
and
the application of an auto
transformer
transformer
configurations.
for reduced voltage motor
Now we're
starting.
going to do a little bit
Remember,
of review
we've
of
already looked
three-phase
at the
power
circuit,
and
but
of
I wanted to
transformers.
make sure that you
And then we're going
understood
to talk
how the
about a
taps
type of
are
transformer called an
used
auto
in the auto transformer coils.
Now there are a number of different places that an
So in
auto
this
transformer
particular
is
one,
used.
rather than
And in a
talking
previous
about turns
presentation,
ratios,
we talked
they
about using an
identified
auto transformer
as
for
the
reduced
percentage
voltage
of
motor
the
starting.
number of turns,
And we talked a
compared
little
to
bit
the
about
total.
how the auto
Okay, so if you
transformer
go between
was able
points A and
to
E,
make a
that's
lower voltage
100%
without being
of
their
full complete transformer.
connection. The
So we'll get
100% of the
into that
coil.
in a
So
little more
100%
depth,
of the
not in the
voltage is
control
between
circuit,
points A
but
and
in
E.
terms of how the auto
Now, if you
transformer
go
itself works.
between
Then we'll talk
B
about
and
three-phase
E, you have
transformers, and the
80% of
two
the coils
configurations
between
that you've
those
learned
2
about
points. So you'll
previously.
have 80%
The
of the
Y
voltage.
configuration between
And the
C
delta
and E, there's
configuration.
65% of
We'll
the
talk
coils.
about the
So
importance
you'll have
of making sure that the
65%
transformers
of the
are
voltage
correctly
and so forth.
phased.
So
So
what
that
we're
we get the
doing
correct
is
voltage
we're
ratios
connecting
at each of the coils of the
auto
transformer.
then
Under
we'll
the
talk
low
about
voltage
several of
operation.
the
Remember, we're
combinations
first
of
starting the
primary
motor
and
at the lower
secondary
voltage.
connections.
In this
of
case,
a
we're using the
three-phase
65% tap.
Then
So
we'll
rather than
actually talk
starting the
about
motor at full voltage at across
calculations,
the
how do we
line
calculate
voltage,
and
then
current
it'll be 65
for Y and delta
Now,
configuration.
what's interesting is how
Then we'll
these
summarize
are connected.
those two
So the 3
configurations
coils
by
are connected
comparing
in a Y
them
configuration
with their
and as we've
mathematical
learned a little bit
relationships.
before, and we're going to cover again, in a Y
We'll then apply
configuration,
the same
the voltage
type
between
of
the phases
to
is
the Y
divided
motor
between the
configuration,
coils, and
it's
the delta
motor
divided in
configuration.
half.
We're going to talk
But
again about the
it
terminals
is
of
using the square root of 3
type of
as the either the multiplier or the divider.
You have a 6
So in
lead
this case,
and a
we
9
have
lead.
line voltage
And
going
then
in
we'll
at
do a little bit of
A
review of power factor
at the A terminals,
because that's an important
and the E terminals
thing
are
to
all
cover when
connected
we talk
together
about
to
electrical
form
power.
the center of the Y. So when you
So as you
have
remember,
voltage applied to
in
L1,
a three-phase
L2, and L3,
power
then
generation
that
system,
480 volts
we have
actually
each of the
divides
phases
across the
120
coils
degrees
at
from each other.
277 volts.
So
across
phase
the coils.
1,
Phase
so what
2,
you're actually
and
doing
phase
is
3
taking
not
are
120 degrees
from
of
the phase
480
before
volts
and the phase after
You're
it.
actually taking 65%
So if you take 3 phases
of 277
and you divide that into
volts.
360 degrees, you get your 120
Okay,
degrees.
so when we have
and the advantage,
that
of course,
condition,
as we've said many
what
times,
is actually
is
across
that
the
at
coils
any one
between
point
A
in time,
and E
there is
connections
no
is
time when
277,
fewer than 2 of the 3
which
phases
is
have
480
current
divided
flowing
by the
through
square
there.
root of 3.
That makes
which
the
is
motors more efficient.
1.73.
It makes,
And you've heard that before.
transformers
So
that are
brand
used
new
in
three-phase
power.
But
But
if we take
efficient as
277 and multiply it by 65%,
now you remember that a transformer
at
uses the
point
concept
C,
of mutual inductance
between C and E, that's 65%
so that at the primary
of the total
we put
current
turns
into it
of wire in
that
each
creates
coil.
a magnetic
And
field
so
that
that'll
then
be
cuts
180
across
volts.
the
So when
secondary
it's
coil.
operating on the reduced voltage or the low voltage connection a conductor,
then you will actually have
a voltage in that
180 volts. We can change voltages by simply using a different number of turns
now that
on the 180 volts
compared to the
that's
number
what
of turns
goes
on the
into
secondary.
the motor itself.
So that would be the
turns
ratio.
at each point.
Voltage ratio and,
so
turns ratio are identical.
We're not operating the motor
So
on 180
we can use
volts.
a transformer to actually
what we're
change
doing
voltages.
is that 180
That's the advantage
volts
of
between
using alternating
C and
current
E
in our power
of the
grid
two coils
and our power distribution
actually
system.
is
And even in
more
our homes,
between
we can have a relatively high voltage
phases
of
going to the
120
motor.
volts. And so we're not going
and
to
we
delve
can bring
that
deeply
voltage
into it,
down
but just
efficiently
know that
into a
it's
much lower voltage
not
that our
180
electronic
volts
devices three-phase
need
going
to
into
do
the
their
motor.
job.
It's greater than
So we
180
can also
volts,
step up
but it's
voltages.
much less
So
than the
that's what
480
you found out
that
with the
normally
power
would go
distribution
into the
system,
motor.
is that once the power is generated, the
So
voltage
this
is
is the way that
increased. It's
circuit
stepped up,
actually
and
operates
that
with the
allows
autotransformer.
us to move
So when you
voltages long
start this up
distances
at
or
a
you
much
first
lower
turn
current
the starter
than
on,
if we were to
then
keep it at the
C3,
line voltage
those
of 120
contacts,
volts,
and C2,
it
those
saves
contacts are
cost,
energized.
and it's
So
also
that
an
puts
efficient
power
way of saving a little
into
bit of
the
power consumption.
autotransformer coils. Now up here,
So
I just drew
some
over the
transformers are
coil
considered isolation
to
transformers.
signify that
They
that
have the
is
same number of
energized and there's
primary
magnetism
and
around it.
secondary turns,
But the
and
voltage will
the
go through
isolation
each coil
transformer
to the
is used for
center
a couple
of
of
the Y.
reasons.
It
Okay, so
isolates
remember
that
the neutral,
terminal A,
which is
is
found
where
in the
C3
primary,
is,
and that
and
neutral
terminal
at some
E
point is
is where
grounded.
C2 is.
And it
And then the
creates
65% tap
same voltage or the
puts
same
that
voltage
lower voltage
at
to
the
the
secondary,
three-phase
but
motor
you
coils.
don't have the neutral
The
associated
time
with it. You
delay
don't have the
timer
ground associated with it.
allows that configuration
Isolation transformers
to
are
work
also
for
used
a certain
when
length
we
of
have
time,
electronic
long enough for the
equipment
motor to come up
like
to speed, or
computers
at
and
least as close
laptops
as
and
we
things
want
like
it that,
that full
that
speed.
use something called a
Once that has reached the end of the
switching power
timing
supply
cycle,
with a transformer
then the
that
next
runs at a
step
high frequency.
is that
Now those switching
C2 and
transformers
C3
have a
open,
way of getting
and
that high
C1
frequency
closes. And then you
back
can see at
into
that
the
point
low
the
frequency
autotransformer
power
is
grid,
no
or at
longer
least
energized, which
inside
is
the
good
building.
because
And
those
that
coils
tends to
are
draw
no
a lot
longer
more
needed.
current
So
through
why waste a
the
little bit of
breaker
power
switches and the
when
wiring.
you don't even need them?
And so if
C1
we have
connects
a
it
computer
directly
lab
across
or a
the
place
line
there's a
to the
lot
motor
of
itself.
so
Computers
that's how
associated
reduced
with it or
voltage
electronic
starting
equipment
works on
with
an
those types of switching
autotransformer
power
starter.
supplies.
Then
So
they will put
on
an
the low
isolation
voltage,
transformer
we have current flow
in the
through the
distribution
autotransformer
system.
coils.
That
We pull the
isolation
voltage out of the
transformer
tap, whichever percent
sort of
we
blocks
select to make
that
it
high
work the way we want it
frequency
to work.
result from
And
the
then once
switching
it
power
gets
supplies
beyond the time
from getting
delay,
back
when
into
we're
the power grid.
we
Confident
don't need to
that it's
change the
going at
voltage.
exactly the right
We
speed,
just need to
and we're
create
ready
an
to have a
isolation
full voltage
of
applied
that
to the
high
motor.
frequency.
Then that's what happens.
Without
that
C3 and C2
isolation
open,
transformer,
C1
we're
closes.
going to
And
create a
if
lot
you
more
want
heat
to, why don't you pause
in
the
the
presentation at
breaker
this point and look
switches,
at the
in the
control circuit
wires,
portion of it,
and a lot
so that
more
you can
load
see
or
how
stress
the
on the
time delay
transformers
contacts
that are feeding
are
that building.
allowing us to connect.
So an isolation
To
transformer you
shift
might
between
think is
C1 and
ridiculous
C2
because it
and
doesn't
also
create a voltage
how
change,
C3
but there
gets
is a
pulled
reason
out of
why
the
we would
circuit
use it.
once the time delay
And then
is
for transformers, you remember
completed.
that the current ratio is the opposite of
So
the
when we
turns
look
ratio.
at power
And the
distribution,
reason for that, as
almost
we talked
never
about in power
in a large
distribution,
building,
whether it's
is
a
not
a
a
large
large
store
or a
but it's
shopping
Watt's law.
center, or it
So
could
as
perhaps
we
be
increase
a strip
the
mall,
voltage,
or it could be a
then
school,
what we
or
end
an
up with
industrial
is
building.
a lower current as
We
a
have
result.
a much higher
And
voltage
that
coming in.
is
It
the
could
reason
be
why the current
7
ratio
to
is
15,000
opposite of the
volts,
turns ratio.
maybe a little bit more, but the power company
Now there is a type
will
of transformer
bring
called
it
an
over
autotransformer,
into
and it's different
the
from a
facility
regular
itself.
transformer in
Now
how
the
it's built,
substation is what
but
is in
it
the
still can
neighborhood or close
function the
by,
same way.
and then that goes into
As you
the
remember
distribution
that a standard transformer
bank that
has a
feeds
primary
the building
coil
or
and a
the
secondary
shopping
coil.
mall, or
Then
the
those
school,
coils
or
are wound
whatever
around a
is
steel core
being powered
or an
by
iron
the
core.
utility.
And
And
that
so you'll have
creates the
something
mutual
like, let's say
induction
in this
between the
case,
primary and
you've got
secondary. We can step
12,470
up
volts, about
voltages or step
12,500
down
volts,
voltages if
and
we
then
have a
the
different turns
distribution
ratio.
transformer
And
breaks it
remember, the
into
current ratio is the
the
inverse
operating
of the turns
voltages
ratio.
that are allowing
Now, a
the
standard transformer
devices
is
that
very
are inside
efficient.
that
You can
building
get
to
about
be
85 to
powered.
90%
So in this
efficiency.
case, this shows
So what that means
if we
is
had
that
a Y,
the power that comes into
circuit,
it,
and
which
it's
is what
let's
you
say
pay
it's a
for
small
when you buy
commercial
electrical
building,
power,
and you want
85 to
operate
90%
the air
of that power
conditioners and the
will go
various
through
other
the
parts
transformer
on
and you're only going to lose
208
10
volt
to
three-phase.
15%
then
as a
that's great.
loss of power
You'll have a
because of the
distribution
transformer.
transformer
Now,
that
there's
has
two
a
reasons why a
Y
transformer
connected
is not
secondary.
100%
Now, if you
efficient.
wanted to
The
go
first
with a
reason
delta,
is
and
that
instead of having
we don't
208
have
three-phase, you had
superconductors. We
240,
have
then
wire
you
that
would
has some
choose or
resistance to it.
wire a
And then in
transformer that
addition,
had the delta
we have
configuration
inductive
for the
reactance,
secondary
and
connection.
those things tend to limit the current and
One of the
also
things
tend
that
to
happens is that
use up a little
on
bit
a
of the
building
power
transformer
that is created.
or
So
one
it's like a
feeding an
resistance will
industrial
have a
plant or
voltage
something,
drop across it.
you often
That
have
voltage drop
the
is a loss of
three-phase
voltage or
transformer
pressure
all built
across the
together as one
device.
unit.
But it will also
So it has
use
three
up
sets of
some of the
coils, three
current,
primaries and
and
three
that's the
secondaries.
challenge
They share the
of
same
any
magnetic
type of electrical device
core
is that we
because
don't have
that helps
100%
make the
efficiency.
transformer more
Another reason
efficient,
why
and it helps
transformers are
focus
not
that magnetic
100%
energy a lot
efficient
better.
is because of
So in
something
this
called
case, we have
hysteresis
one
loss.
transformer
A
that
hysteresis
is a
loss
three-phase
is
transformer.
a
We can connect the
loss of power
primaries and the
because
secondaries
the
as either
core of
delta
the
or Y,
transformer
and that
needs to become
combination
magnetized.
of and then
Configuration,
that
in
energy that
addition to the turns
magnetizes it
ratio of the
when the
transformer, will
voltage drops
determine
down
what
to
voltage
zero
we have
and
coming
the
out
polarity
into the
reverses,
facility.
because remember, transformers are only
So,
able to
because there are
operate
4 different
on alternating
configurations, we
current
can have 4
or
different
pulses
combinations
of direct current.
we have 2.
You can't have a
The
complete
Y and the
smooth
delta
direct
if
current
you
through
take
it.
2
So when
squared,
the
that's
transformer
4
reverses
combinations.
its
So we have 4
magnetic
combinations
polarity,
possible.
then all of
And
those little
by using
molecules of
a
iron inside
different
the core
type
need
of
to move
configuration in the
themselves around
primary, then we
180
do the
degrees,
secondary so
we
that
can
it
get
can
a
be
wider range of
magnetized in the
voltages
opposite
from
magnetic
the
polarity.
transformer.
So those little
And that helps out
molecules
really
are held
well
in
because a lot of
with a
times
certain amount of
these
energy. So it
transformer
takes up
units
or it
are
utilizes,
multi-purpose.
it
And
uses
so they will
up
have
some
different
of the
taps that
electrical
not only
power
can you
to
use the
literally
taps to
rotate those
create exactly the
molecules
voltage range you
in
want,
that
depending
bar
upon what
or
the
those
voltage coming
slices
into the
of steel
transformer is,
that
but
are
also by
making up the
changing
transformer
whether
core.
the primary is a delta or a Y and
Now,
the
with an
secondary is a delta or
autotransformer,
Y,
they only
then
have
you
a
can further
single
get a different
coil,
set of voltages.
and that single
So
coil
that's
has
good.
multiple
Now, one of the
taps in
things
it.
we
Is
can
the
step up voltage with an
reason why we would
autotransformer.
choose
We can
each
step
of
down a
those
voltage with an
configurations.
autotransformer. Delta has some advantages,
It
Y has some
has the same
advantages.
coil that
Y
is much
will work
easier to
as a
make
multiple
primary and as a
voltages,
secondary,
like
but you'll
120 and
notice on the
208,
way that
than a
these are
delta.
wired
Now, a
is that
delta
there
is
is
good
one
because
connection
it is
point
more
that is
reliable.
electrically
A
common
delta will still
between the input
function
side and the
if we
output side.
disconnect,
It's
or if
the
one of the
line
coils
that's
burns
shown
out.
at the
The
bottom
other two
of
coils will
those
keep all three
diagrams. You'll
phases
see those little
energized.
um,
And we call that an
connection
open
points.
delta, and you'll
The
see
power
that in
comes
just a little
in,
bit.
and then the voltage
In
comes
a Y
out.
configuration,
One of
the
those
center
connections is electrically
connection
common.
of the
So
Y
we don't
is
have
where
the
one side of
isolation
each of the
of the
coils
neutral
is connected.
connection.
The motors that we use in our
Oftentimes,
lab
it's
are all
very
connected
beneficial
in
to
Y
connect the neutral
configuration.
to that
We had a
bottom
lab where we
common
used
connection.
a delta
But then
configuration,
the neutral,
and
which is
that
grounded
created
at
a
some
higher
point,
voltage into
also
the
means
motor, and
that
we
the
just did
other
that
side of the circuit,
for a very
the
short amount
load
of
side
time.
of the circuit,
But
also
if
has
we
that
had a motor
grounding
connected
that
the wrong
remains.
way,
Just
so
like if we
sometimes
had
that
the
grounding
transformer
or the
connected the
neutral
wrong
being
way,
in the
we
circuit
could get
isn't a
either
problem.
a much lower
And in that
voltage than we
respect,
wanted
the
or a much
trade-off
higher
with an
voltage
autotransformer is
than we
actually a
wanted.
good thing.
So in a Y
Because you
configuration,
find that an
the
autotransformer
voltage
is much
across
more
the
electrically
coils,
efficient. You'll see that the
95 to
coils are in
98%
series with each
efficiency
other
in an
between
autotransformer.
two of the phases.
So one of the reasons why they would
We
use
don't
an
just add them
autotransformer
up.
in the
We don't
electrical
have half
power
of the voltage going
distribution
across one
system
coil
in the power
and
grid
half going across the other
is that
coil.
they can
If
boost
we
the voltage up a
lost
little bit or
one
they can
of
drop the
the
voltage down a
legs,
little bit.
then that's
Those are
exactly
called
what would happen.
regulator banks.
And by legs, I mean
But
one
by
of
using an
the
autotransformer,
line
they don't
connections.
lose as
If I
much
lost, for
wasted
example, line
power.
C,
And remember,
that's what
then
PG&E
I
or
would
any other
have
utility is selling to
half of the
you
voltage
is
across
electrical power.
the
And
coil between A
if
and the center,
every
and
time
half
it
the
goes
voltage
through
across B in
wires
the
or
center.
through
But by putting
transformers or
3
various
phases
other
in it
parts of the
and
system,
having that
there's a
phase
little bit
shift
of
of
power
120
loss over
degrees
time. That
between
is
each
a lot of
phase,
loss,
it
and
means
they
that
don't get money
we
for
don't
that.
have
It's just
equal
like taking a pipeline and poking holes in it every so often and
we
having the
don't have
liquid
equal
leak out a little
proportion.
bit from
And what
every hole. When
proportion
you
would
add up the
say is
total
that if you
leakage,
had 2
you're
coils that
losing
were
a
equal
significant
in
amount
the
of
number of
product.
turns,
So
then you
auto
would have
transformers are
exactly half
used
the
in a
voltage
number of
across
different
each of them.
ways.
But what
In
I
this
wanted to
case,
show you is
you would
how
we
have
can actually take one
the square root of
coil
3
and use it
into
to
it.
create a step up
And
or a step down
we
voltage.
either multiply by the square root of 3
There's a
or
version
divide by
called
the
an
square root of 3,
variable auto
depending upon if we're
transformer.
going from
The
line to
trade
coil
name of
or
those
from
are called
coil voltage to
variacs.
line voltage.
And that is
Now,
the
in a Y
trademark of a
distribution
company called
system,
General Radio
current is
that
the same.
really
So whatever is
not they may
flowing
not have
through
invented them, but
for
they
example,
got
that
to
top
where they're really
coil,
good
the one that goes
at
between the
making them.
center and
And they
connection A,
sold,
let's say 20
you
amps were flowing through
millions
that
of them
coil,
over the
the same
years.
20 amps
If
would
we
be
want a
flowing
variable
into and out of point
voltage
A.
in
The
alternating
same thing
current
here with
that we
B
don't
and C.
want to lose
So the
any
line
or
voltage and the
significant
phase
amount of
voltage are
power,
the same.
then we can use an auto transformer. And some auto transformers can even be connected so that you can get more than 100% of the incoming voltage. When they wanted to make in theaters and auditoriums and stages where we had concert lighting, before we had a lot of solid state devices, the transistors, the SCRs, the triacs, those things, this was the way they dimmed the lights in those theaters, was with an auto transformer. I'll show you how they're used in motor starting in a little bit, but you can see that this is a 2-coil version of an auto transformer, and you'll see that there are multiple taps, multiple connection points. So they'll wind a number of turns and then they'll come out to a tap, and then they'll come back with another number of turns, they'll come out to another tap, then they'll come back and do another number of turns and so forth until they get the number of taps that they want. So we'll see that in just a minute. I'll kind of put that on the back burner for just a second here. As we said, that one of the reasons why an auto transformer is used is because it's very efficient power-wise. So if we used one in a regulator bank, a voltage regulator, then that's a lot more efficient than trying to change the taps in a regular transformer that has 2 coils to it per phase. So essentially what they'll do is that the voltage of the power line can change up to 20% during the day as more customers start turning on their electric appliances. It starts drawing more power out of the grid. A good thing to do would be to try to adjust the voltage at the generating station. The downside of doing it that way is that the generating station is always or usually hundreds of miles away from where the electrical power that's being generated is actually used. So if you increase the voltage at the generator to make up for a voltage sag 200 or 300 miles down the road, the people that were close to the generator, their voltage would be too high. And likewise, if you reduce the voltage at the station that's close to the generator, then there'll be a lot more voltage reduction down the road. And so what they'll do is they'll put these regulator banks in the power grid at various stations throughout the geographical area. And they have motorized contacts that can switch between the various taps. So they can boost the voltage a little bit or they can drop the voltage a little bit. And how much they boost it or drop it depends upon which taps they tap into on the auto transformer. You'll see how that works when I talk about using auto transformers for um, a reduced voltage starting system. So the way that an auto transformer can work, it can be used as a step down transformer or a step up transformer. So essentially with step down, we tap into the auto transformer coil below the maximum. So this actually is creating two different sets of coils. The whole thing, the whole entire coil is considered the primary. But then the secondary is a portion of that coil. So the part between the two connections on the secondary is considered the secondary winding, and the whole thing is considered the primary winding. This is like having a couple of resistors in series with each other. Okay, let's say that you have one resistor that is 3,000 ohms, and then you have another resistor that's 1,000 ohms. The voltage will divide across the total resistance proportional to the resistance value. So the 3K is going to have 3/4 of the voltage across it. The 1K will have 1/4 of the total voltage across it. Now, we're not talking that there is an equal connection between a resistor and an inductor that's used in a transformer. They function the same way in the sense that they create voltage division, voltage divider. But the reason that the transformer is able to divide the voltage up is not just because of the resistance of the wire, but the magnetic induction that's created by the coil of wire. So the turns ratio between the two will determine what the voltage is coming out of the secondary. If I had this, let's say this was 4,000 turns, 3,000 of the turns were across the secondary and 1,000 turns were across the primary, then the voltage would divide in proportion to the turns ratio, or the number of turns. So 3,000 out of the 4,000 across the secondary makes 3/4 of the voltage at the secondary compared to the primary. This 1/4 up here of the turns would have 1/4 of the applied voltage, the primary voltage across it. So you can see that turns ratio works in auto transformers as well as it does with standard transformers. And the turns ratio and the voltage ratio are still identical in both of these types of transformers. Now, it's interesting because we can connect the primary circuit, the power source, to a portion of the total windings. And that could create a step up situation. So, for example, if I have again 4,000 turns and 3,000 of those are across the primary, then that would be considered the primary turns ratio, 3,000. And then across the secondary, the whole coil becomes the secondary winding. There's 4,000 across here. So let's say I had 100 volts coming in. Then what I want is I'm going to have across the primary, I'm going to have 100 volts across there. But across the secondary, I'm going to have 1/4 more voltage. So 1/4 of 1,000 is 25. So I would actually have 125 volts across the secondary because of how the turns ratio is set up. Now, a multiple tap, this really kind of shows you the difference between the number of turns and how we determine the voltage across it. So let's say that between D and E, there's 60 turns. Between C and E, it's now 160. Between B and E is 240 turns, and then there's another 40 turns. So between A and E, there is 60 and 40 and 100 and an 80. So that's 280 turns. So what we can do is we can actually use those numbers to determine how much voltage there is. So if we have 120 volts primary between B and E, and let's say there's 240 turns, then the way that we calculate that is actually how many turns per volt there is. So there is actually 2 volts or 2 turns for every 1 volt. So to find the voltage, we can multiply the number of turns times 2, and that will give us the voltage that we have coming out of the transformer. So remember, the whole entire primary is from E to B. But if we go between any two of these, we can get a multitude of different voltages. So this 120 volts actually will divide in proportion to the number of turns. So across the 80 turns, we divide 80 by 2 because there's 2 turns for every volt, and that will mean I have 40 volts between B and C. Between C and D, if I take 100 divided by 2, that's 50 volts between C and D. If I take 60 turns divided by 2, that means that there's 30 volts between D and E. So if I connect C and E, then I would have 30 plus 50, which is 80 volts. If I went between B and D, for example, then there would be 40 plus 50, which is 90 volts. Okay, so I could run this 120 volts. If I used E as my 0 point, I can get 30. I can get 30 plus 50 is 80. I could get then the full voltage, which is my 120 if I went between B and E, or I could even get above that. So the voltage between A and B is 20 volts. So if I have 120 volts going in, but I connect the output between A and E, then I actually have 140 volts. So that creates a step up transformer. So again, it all has to do with the number of turns between the taps that I'm connecting to. All right, so I can't figure it out based on these 40 turns that are above where the power supply is connected. I have to figure the amount of turns per volt between B and E. But the same rule, the same number of turns per volt will apply to A and B. One of the good things that we have with the autotransformer is being able to switch between the various taps. And by connecting to the various taps, I can make the voltage lower or higher than the power coming into it, the voltage coming into it. The current in an auto transformer, in the primary side, the current is the same throughout all parts of it. The current through the secondary side is the same through all parts of it. So what happens is that it depends upon the turns ratio, but it's opposite. In this case, I have 480 volts coming in. I only have 240 volts coming out. So that is a 2-to-1 turns ratio. The current ratio is the inverse of that, the opposite. The current ratio is 1-to-2. So the 2 amps in the secondary multiplied by 2 gives us 4 amps. Or we could also say for every 1 amp that flows in the primary, 2 amps will flow in the secondary. So now you know how the auto transformer operates. Here is the application of an auto transformer for reduced voltage motor starting. And remember, we've already looked at this circuit, but I wanted to make sure that you understood how the taps are used in the auto transformer coils. So in this particular one, rather than talking about turns ratios, they identified as the percentage of the number of turns compared to the total. Okay, so if you go between points A and E, that's 100% of their connection, the 100% of the coil. So 100% of the voltage is between points A and E. Now, if you go between B and E, you have 80% of the coils between those 2 points, so you'll have 80% of the voltage. Between C and E, there's 65% of the coils, so you'll have 65% of the voltage, and so forth. So what we're doing is we're connecting the autotransformer under the low voltage operation. Remember, we're first starting the motor at the lower voltage. In this case, we're using the 65% tap. So rather than starting the motor at full voltage at across the line voltage, then it'll be 65%. Now, what's interesting is how these are actually connected. So the 3 coils are connected in a Y configuration. And as we've learned a little bit before, and we're going to cover again, in a Y configuration, the voltage between the phases is divided between the coils. It's not divided in half, but it is using the square root of 3 as either the multiplier or the divider. So in this case, we have line voltage going in at the A terminals, and the E terminals are all connected together to form the center of the Y. So when you have voltage applied to L1, L2, and L3, then that 480 volts actually divides across the coils at 277 volts across the coils. So what you're actually doing is taking not 65% of 480 volts. You're actually taking 65% of 277 volts. Okay, so when we have that condition, what is actually across the coils between A and E connections is 277, which is 480 divided by the square root of 3, which is 1.73. And you've heard that before, so this shouldn't be brand new to you. But if we take 277 and multiply it by 65%, which at point C, between C and E, that's 65% of the total turns of wire in each coil. And so that'll be 180 volts. So when it's operating on the reduced voltage or the low voltage connection, then you will actually have 180 volts at each across each coil. Now that 180 volts, that's what goes into the motor itself um, at each point. And so we're not operating the motor on 180 volts actually. What we're doing is that 180 volts between C and E of the two coils actually is more between two of the phases going to the motor. And so we're not going to delve that deeply into it, but just know that it's not 180 volts three phase going into the motor. It's greater than 180 volts, but it's much less than the 480 that normally would go into the motor. So this is the way that circuit actually operates with the auto transformer. So when you start this up, or you first turn the starter on, then C3, those contacts, and C2, those contacts are energized. So that puts power into the auto transformer coils. Now up here, I just drew over the coil to signify that that is energized and there's magnetism around it. But the voltage will go through each coil to the center of the Y. Okay, so remember that terminal A is where C3 is, and terminal E is where C2 is. And then the 65% tap puts that lower voltage to the three-phase motor coils. The time delay timer allows that configuration to work for a certain length of time, long enough for the motor to come up to speed, or at least as close as we want it to full speed. Once that has reached the end of the timing cycle, then the next step is that C2 and C3 open and C1 closes. And then you can see at that point the auto transformer is no longer energized, which is good because those coils are no longer needed. So why waste a little bit of power when you don't even need them? So C1 connects it directly across the line to the motor itself. So that's how reduced voltage starting works on an auto transformer starter. So on the low voltage, we have current flow through the auto transformer coils. We pull the voltage out of the tap, whichever percent we select to make it work the way we want it to work. And then once it gets beyond the time delay, when we're confident that it's going at exactly the right speed, and we're ready to have it full voltage applied to the motor, then that's what happens. C3 and C2 open, C1 closes. And if you want to, why don't you pause the presentation at this point and look at the control circuit portion of it so that you can see how the time delay contacts are allowing us to connect, to shift between C1 and C2, and also how C3 gets pulled out of the circuit once the time delay is completed. So when we look at power distribution, almost never in a large building, whether it's a large store or a shopping center, or it could perhaps be a strip mall, or it could be a school or an industrial building, we have a much higher voltage coming in. It could be 7 to 15,000 volts, maybe a little bit more, but the power company will bring it over into the facility itself. Now, the substation is what is in the neighborhood or close by, and then that goes into the distribution transformer bank that feeds the building or the shopping mall or the school or whatever is being powered by the utility. And so you'll have something like, let's say in this case, you've got 12,470 volts, about 12,500 volts, and then the distribution transformer breaks it into the operating voltages that are allowing the devices that are inside that building to be powered. So in this case, this shows if we had a Y circuit and let's say it's a small commercial building and you want to operate the air conditioners and the various other parts on 208 volt three phase, then that's great. You'll have a distribution transformer that has a Y connected secondary. Now, if you wanted to go with a delta, and instead of having 208 three phase, you had 240, then you would choose or wire a transformer that had the delta configuration for the secondary connection. One of the things that happens is that on a building transformer or one feeding an industrial plant or something, you often have the three-phase transformer all built together as one unit. So it has three sets of coils, three primaries and three secondaries. They share the same magnetic core because that helps make the transformer more efficient and it helps focus that magnetic energy a lot better. So in this case, we have one transformer that is a three-phase transformer. And we can connect the primaries and the secondaries as either delta or Y, and that combination of configuration, in addition to the turns ratio of the transformer, will determine what voltage we have coming out into the facility. So because there are four different configurations, we can have four different combinations, or we have two, the Y and the delta. If you take 2 squared, that's four combinations. So we have four combinations possible, and by using a, a different type of configuration in the primary than we do the secondary, we can get a wider range of voltages from the transformer. And that helps out really well because a lot of times these transformer units are multi-purpose. And so they will have different taps that not only can you use the taps to create exactly the voltage range you want, depending upon what the voltage coming into the transformer is, but also by changing whether the primary is a delta or a Y and the secondary is a delta or Y, then you can further get a different set of voltages. So that's good. Now, one of the things is the reason why we would choose each of those configurations. Delta has some advantages, Y has some advantages. Y is much easier to make multiple voltages like 120 and 208 than a delta. Now, a delta is good because it is more reliable. A delta will still function if we disconnect or if one of the coils burns out. The other two coils will keep all three phases energized. And we call that an open delta, and you'll see that in just a little bit. Okay, so let's get into the Y-configured distribution system. Now there's two terms that you'll see used throughout the rest of this presentation. It's line and phase. The line is actually each power line in the three-phase circuit. So that would be L1, L2, and L3. Phase is the voltage across the load or the component. In this case, the phase voltage is the one that's across the coils. Okay, so if If we had, for example, 208 volts in our line voltage, that's the voltage between L1 and L2. Let's say we connected L1 to A, L2 to B, L3 to C. The line voltage would be the 208 volts. The phase voltage would be the voltage across the coil. So the line voltage is the square root of 3 times E phase, the phase voltage across the coils. Or we could say that the phase voltage is equal to the line voltage divided by the square root of 3. Okay, so that would mean that a 208 line voltage would be 120 phase volts. Okay, so how the current works is that, let's say there is 20 amps of current flowing through each of the coils, each of the phases. Then that same 20 amps of current that flows through this one, for example, will also flow into and out of the line, the L1 connection, if that's what is connected to terminal A. So the voltage, you have to use the square root of 3, but the phase current and line current are the same. Now, one of the advantages of a Y configuration is that we can pull a neutral out of the center. So if we go between any of the 3 lines, A, B, or C, and the neutral, then we get the same voltage that's across the coil, the phase voltage. So if we go, for example, between C and N, we're going to have the same voltage that's across this particular coil. Now, for safety purposes, the neutral is grounded at some point. So by having a ground at the neutral connection, that grounds the center of this transformer bank, the coils, and that is a more safe way of operating. If something came loose, then it does not necessarily have the wire come in contact with the frame of the transformer, which will probably be grounded. But it also, if it comes loose and tries to connect to one of the other phases, you're going to either have a phase to phase, which would trip a breaker switch, or you have a phase to ground, which is going to trip the breaker switch. So grounding the neutral is important for better safety. The motor or the transformer does not need that center connection to function, but there are advantages of making that the neutral connection or grounding it. So this is how the voltages work in our labs. So if we were to measure between a line and neutral, we would have the phase voltage, which is 120. If we went between the line and the other line, we would have the 208 volts. Now this is good because what we can do is spread out the single phase loads across the different lines that are coming out. That tends to balance the current through each of the coils, and therefore the neutral, if they are all balanced, then the neutral is not going to have any current flow. Well, the problem then happens that if you had each of these loads had a different amount of draw of current on the transformer, then you would have a neutral current. Now, how you calculate that neutral current, you can't just add them up because you have 3 phases that are part of the power line, but then you're pulling from one phase to neutral. And each of those 3 phases is 120 degrees from the phase next to it. So there is a formula that you use, but we're not going to cover that for this part of our class. Here's the 208. Remember, if we go across the line voltages, we get the high voltage. Now, a delta configuration is the opposite of a Y in terms of the math involved. For a Y, current was the same. For a delta, voltage is the same. So the line voltage and the phase voltage would be the same value. Remember that what the phase is this the voltage across the coil. The line current and the phase current are where the square root of 3 come into play. So if I knew the phase current, I would multiply by the square root of 3. That would give me the line current. If I knew the line current, I would divide the line current by the square root of 3, and that would give me the phase current. And as I said, the delta configuration is more reliable because if I lose any one of these three coils, it would still give me the right voltage coming out. Now, the voltages in a Y configuration are generally higher than those in the voltages in a delta, are generally higher than the voltages in a Y configuration. The problem with delta is that if I wanted to run a neutral to be able to get half of the voltage, then I have to use a center tapped coil on one of these, and that's where I would connect my neutral. So across the two ends of the coil, I have the same voltage that I have between the lines. So that would be 240. So if I did a center tap on this coil, then I would have 120 and 120. And the reason I can do that and not have to use the square root of 3 is because each of these coils is their own phase. So if I just go between the edge and the center of either side of a coil, that's single phase. So that will work to allow my neutral connection. So I can get a high voltage and a low voltage from a delta configuration, but I have to have a transformer that has center taps. The problem is that if I connect between the wrong phase connection and the line connection, or so if I use the center tap, if I went between the center tap and either B or C, yes, that's good. If I go across the same phase, the same coil. But if I go between the center tap and a different tap, which would give me, let's say I go between neutral and A, then I would have a magnetism across this coil, and that's going to give me a certain voltage across it. And then I would have an additional voltage between B and the center tap. So I would actually get, instead of 120 volts, I'd get 195 volts. Now that's pretty close to the 208 that are between A and B, or B and C, or A and C. The reason that it's not 120 plus 208 or some other thing is because the coil between A and B is at a different phase angle than between B and neutral, or between B and C. So that gives me something called a bastard voltage. Now that's, the term bastard is not very politically correct. It just means kind of an orphan, or a voltage that isn't part of the standard system. But I also think it's a good name because if you wired it up the wrong way, then things would blow up and they would call you the bastard. Now, when you connect three-phase transformers, if you're connecting them Y or you're connecting them in delta, The phasing of the transformer is very important because the polarity of the electromagnetism that happens, the magnetic polarity, the north and south, have to be in such a way that they are working together and not working apart from each other. So what we want is we want them connected so that um, when the three-phase power comes in, that three-phase power has the correct polarity at that moment in time. Because remember, AC is, it has polarity. It has a positive and a negative, but that alternates 180 times, I'm sorry, yeah, 120 times per second. Got to stop doing these lectures later in the evening. So anyway, it's important that the coils are connected in the proper configuration. And that is what we call phasing of the transformer. Phasing simply means that if I stop the sine wave coming into the transformer at one moment in time, then I'm going to have a polarity. Let's say that the top is positive and the bottom is negative. Well, what would happen on the secondary side? Is that going to have the same polarity that it does on the primary side, or will it be opposite in polarity? That is phasing. So phasing is identified on a schematic diagram in form of dots. Those are called phasing dots. And so if the dots are on the same side of the coil on both the primary and the secondary, then that means that the output is in phase with the input. So we compare the two and they are 0 degrees phase shift. They are in phase. If for example, it's wound so that the dots are on the other side, opposing sides, then the phase shift will be 180 degrees. So it will be opposite. So when this up here is positive, this up here is negative. When this down here is negative, this is positive. When you connect one or two of these transformers where the phasing is opposite from the other one or the other two, then you're not going to have the correct voltage distribution across those coils. So it will not be even if you measured between L1 and L2 or an output, for example, of a transformer. You're not going to get the same voltage as if you measured between L2 and L3. And you're not going to get the same voltage if you measure between 1 and 3. So that phasing is vital. Generally, when they build the transformer, they have it set up, it's pre-wired so that the phasing is correct. But if you're connecting three individual transformers to make a three-phase assembly, then you have to be careful which is the correct phase and to connect them together properly. There is a unit that you can buy that actually connects to a transformer in the primary and the secondary to determine the phasing. But if you don't have that unit, you'll do what we do in the three-phase transformer lab, and that is we use a jumper between the primary and the secondary. We apply voltage to the primary, and then we measure the voltage between the primary and the secondary. And if the voltage is greater, it is out of phase. If it's a lower voltage, it means it's in phase. So remember, you see the pluses up there at the top, and then this is a plus and a minus. That is a polarity of the input AC coming in stopped at a moment in time compared to what the polarity is at the output at that point at that same moment in time. So in phase means that the polarity is the same on both sides. Out of phase means the polarity is opposite when you compare the two sides. So you see here, this is a Y to Y configuration. Both primary and secondary phasing dots are on the same side, and therefore you're going to get a predictable voltage at the output, and it will be the same whether you go between A and B or B and C or A and C. It should be the same. Or if you go between A and neutral or B and neutral or C and neutral. So phasing is critical. If it's wired up incorrectly, then those voltages will not be equal like they should be, but one voltage will be greater than the other. And in addition, it's going to change the amount of current that flows through the coils. So that will have the additional disadvantage of putting more load into the transformer itself. So when we connect Y to Y, remember that we have one side of the transformer, of each transformer itself, connected to a common point. That's our center point, and that would be how we would get the neutral. And then each transformer's other side is connected to one of the three phases. So this is what a Y to Y configuration looks like. Now, to figure out the exact voltage between A and B and C and A and C, which would be the line voltage, or what the voltage across the coils, which would be the phase voltages, we would have to know what voltage we have coming in. We'd have to know that it is a Y configuration coming in. We'd have to know that the turns ratio between the primary and the secondary. And by the way, all three of these transformers must have the same turns ratio. Even if we had center taps or various other things, we have to use the same amount of turns ratios on each transformer on the primary and the same turns ratio on each secondary of the transformers. Here is a delta Y configuration. We sometimes power lines that are going into neighborhoods and into distribution centers, a lot of times they will be wired up in a delta configuration, and that is for reliability more than anything else. So the system was designed with a delta on the primary side. On the delta configuration, you see that you have one side of the transformer going to one of the lines, the other side of the transformer going to the second one in series, and also to a second line. And then that second transformer goes to the third transformer in series and connects to yet another line, and then the first one starts at the opposite line. So you can draw this out in a picture, and you would see it would look like the delta, the triangle. Now the Y side is where a lot of distribution systems, the secondary are wired in a Y configuration, and that gives you the neutral. Because remember, if we had like delta to delta, the secondary would have to have center taps. And the problem with that is that one transformer would use a lot of current or create a lot of current, the one that had the center tap in it, whereas the other ones would only be used for a three-phase motor or a piece of equipment that ran on three phases. So in this case, by using a Y configuration, all three transformers feed the same neutral. So if we balance the single phase loads, the lower voltage loads between neutral and A and then neutral and B and neutral and C, then the current would be pretty even on the three transformer coils. So that's an important reason why the output is most commonly Y rather than delta. And then here's the delta delta, and you can see that these transformers have no center tap. So they're only able to create three phase. They don't have the ability to create single phase unless the single phase is between two of the lines, like between A and B or between B and C, so forth. As we said, the reason that we would use deltas not only for the correct voltage ratio, but also, so now let's look at the open delta. In this case, for simplification, we're just looking at two of the transformers that are connected both sides as delta. We can't really do a Y side for the secondary if we have open delta because the phases are not going to be correct. So only with an open delta can you have a situation like this where you have the secondary, in other words, has to be the delta. Now, for cost effectiveness, sometimes they'll use two transformers rather than three. And when those two transformers are used, they have to buy transformers that can handle that extra amount of current because you're going to pull more current through each of the transformers because instead of being divided among three transformers, you're dividing the current by only two. So the advantage of a regular delta configuration is that if one of these transformers went bad, then you could take it out of the circuit and the thing would still operate. It would operate more current through the remaining two transformers, but it will still get you through until you had a replacement transformer installed. Well, if you take a look at how the open delta is connected, one transformer is connected between one phase and the second one. Those two are connected in series with each other. The third connection, which is in this case connected to the A phase, completes the circuit. Now, we can't put a wire between this one and this one to close the delta because if we did that, we would have a short between A and C. Now, that was what this picture originally was drawn like, to show you that when you take the third transformer out, you basically need to remove any shorts that could happen so that you don't have that situation. Now, if you lose one of these transformers, then you're not going to have correct voltage across the lines because you only have single phase, and that's going to be a problem. So if one of the two transformers were to fail, then you would have a big issue. Now, there is a mathematical calculation to determine what the phase voltage is and the line voltage is and everything. And interestingly enough, it's the same. So the voltage across the coils would be the same as the voltage between two of the lines. But the current is a different story. So the current has to be calculated using not only the square root of 3, but also it has to be calculated knowing the phase shift that would be happening at the transformers. And so that's more complicated. That's beyond the scope of what we're going for in this class. Now, this is actually some transformers that are part of a generating station. And you'll notice that there are banks of transformers. So there are 3 individual transformers connected to each generator. And they're in some type of a 3-phase configuration we don't know by looking at this because it's not a very clear picture, but it's either delta or Y. And you can then take that, steps up the voltage from the generator voltage into a voltage that brings this into a large power substation. So here is a comparison of the voltage and current calculations. I'll show you that again in just a minute. Remember that the conductors are the lines, the components, the loads are called the phases. Line voltage is between the two lines. The phase voltage is across each component. Line current is the current that is coming into or out of the lines connected between a three-phase source and the load, and the phase current is through any component, a coil, whether it's a motor coil or a transformer or something like that, comprising a three-phase source or load. Okay, so in a balanced circuit, then you know that these are the mathematical relationships. An unbalanced circuit, you're going to have some other factors that factor into the calculation. So again, delta, this is your mathematic relationship with an example for both the line and phase voltage and the line and phase current. In a Y, these are the mathematical relationships, and there's some examples of calculations with actual values that are used. And so the difference, as you remember, between delta and Y are the voltage in one has the square root of 3 involved, the voltage in the other is the same. The current in one is the same, the current in the other one has the square root of 3 involved in it. So for the upcoming exam, you've got to make sure that you remember what those are, because those formulas will not be given to you. You'll have to have them in your brain. Remember the square root of 3. There's 3 phases. Your calculator hopefully has a square root button, and either you multiply them or divide them depending upon if you're finding line or phase. Okay. So this is working through using the voltages in our lab equipment, and that shows an example. Now, when we apply Y and delta configurations to a three-phase motor, it's identical to what happens in a transformer. When we connect Y motors together, sometimes we have a dual voltage motor. So that has 2 sets of coils. Now the coils for each phase can either be wired in series with each other or in parallel with each other. In this case, this is a dual voltage Y motor that is not pre-wired to a lower or higher voltage. If we wanted to run the motor at a higher voltage, then we would put them in series. Because the phase, these 2 coils are in series with each other, then the voltage will divide equally. Even though we have 3 phases coming into it, we're only working with 1 phase and 1 line at this particular location. So if you had a 240 480 dual voltage motor, if I'm running it at 480, then I'm going to put the windings in series, and this is what you see here and how they're connected together numerically. If I'm doing it in a lower voltage, then I'm connecting them in parallel. So I connect 4, 5, and 6 together, 1 to 7, 2 to 8, 3 to 9. This one shows the one way of looking at it. This shows another way of looking at it. They're both electrically identical. They're just drawn in a different method or a different way to show you how those terminals are connected together. Now remember that T1 is going to be the same for various motors. And so those number systems on terminal numbers for motors are the same. This is the same way of doing the voltages across. And in this case, instead of doing dividing by the square root of 3, we could multiply by the reciprocal of the square root of 3. So the square root of 3 is 1.73. If we take 1 over 1.73, we're going to get 0.5773. So most technicians simply remember 0.58 as the number. So rather than dividing by the square root of 3, we multiply by 0.58. That's all this slide is telling you. This is what happens when we're running the motor at the higher voltage. Then even though the 480 volts will divide between each set of coils at 277, 278, depending upon how far you take out the decimals when you do the math. That 278.4 is actually half and half across each coil in that phase. Now in a delta motor, you'll buy a motor that has these connections already made between the coils. Then that's for T1, T2, and T3. A motor is pre-wired for either delta or Y operation. In this case, it's pre-wired for delta. The motor that we had before was pre-wired for Y. Okay, so you'll notice that one side only of one set of 3 coils is connected together. So that's pre-wired to operate as a Y configuration. Then you can make it either lower or higher voltage. Now the delta, notice that 2 of the coils are connected together to a terminal for each of the 3 phases. We can't take a motor like this and run it either Y or delta. We have to choose the one that it was wired at. In order to make a motor work with either Y or delta, we need one that has each coil separate. So this has 9 leads on it, but one of those kind of motors, they call it 12 lead because each coil has 2 wires connected to it. There's 6 coils times 2 wires, that's 12 wires or 12 leads. So remember, this is what a Y looks like compared with a delta. The terminal numbers are similar in how they're used, but how they are connected in low and high voltage is different. Okay, so in a delta, when we're running it in the high voltage side, we're connecting them in series. So we have a wire between 6 and 9, between 4 and 7, between 8 and 5. If we are running it on the lower voltage, we're going to connect these connections so that we put those pairs of coils in parallel. Okay, so that's how we would do it. Now when you buy a motor that's a dual voltage motor, you usually take the cover off of the terminal box, and on the inside of that cover it has exactly a map on how do you wire it for lower voltage or for higher voltage. So if you don't know that, if that plate is missing or for some other reason, there are a lot of reference books that have that. There are apps on the smartphones that you can look it up as well, or you could just look it up online. But remember, a motor is either wired internally to be delta or Y. And so the Y coil voltages would be in series, the voltage divides, the line voltage will divide. This says Y motor coil voltages. This should say delta. I'm sorry about that. Just noticed that. But in delta, you're going to have the same situation. In the higher voltage, the voltage will divide across the two coils. In parallel, it will be the same across both coils. This is the 12-lead motor that I was talking about. It allows you to do the Y delta starter on both either a lower voltage or a higher voltage. So in the Y start, we connect everything up so that our motor coils are connected in a Y. Once it's gotten up to speed, then we turn it into a delta configuration. Now again, you'll notice that the coils are in series. So that's using the motor on the higher voltage operation rather than the lower voltage operation. We start with a Y configuration because the voltage across the phase completely is less than the line voltage. Once it's up to speed, the voltage across the coils is the same as the line voltage. So phase equals line. And coil voltage on these slides, coil voltage means phase voltage. The final piece of the puzzle is to review power factor. Now we've touched on it a couple of different times, so we might as well just do a final review of power factor. So there are actually two different powers, actually three if we count the um, reactive power. But in this case, if we multiply voltage times current using Watt's law, we have something that's called the apparent power. If we measure with a watt meter how much power is actually used by the motor, and therefore how much power we're actually purchasing from the utility, then that's true power. So these are not the same unless you have just resistance. If you have reactance because of the coils of the wire, or if there are capacitors in the circuit, then it's going to be different. So power factor is simply a comparison of true power divided by apparent power. Now, power factor, a perfect power factor is 1.0. So if you have less than 1.0, then you have a percentage or a decimal fraction. In this case, we're converting a decimal fraction to a percentage. The closer it is to 1.0, the better. If it were a perfect power factor of 100%, then the amount of current that it's actually drawing is equal to the amount of current you're expecting to draw. And therefore, you're in good shape. The lower the power factor, the more current will actually be pulled through the power lines and through the wiring and the breakers or the fuses, and that creates a problem. So we correct power factor by either using a synchronous motor that has a power factor that's actually a leading power factor. The number itself is not going to be greater than 1 if we do the math in the correct version. But if we have a power factor deficit of, let's say, 15%, if it has a power factor of 85%, then you can run a synchronous motor that has, if that had a leading power factor of 15%, it would make up for the deficit. So large pump motors that are used in irrigation and moving water long distances in a distribution system for water, they have large synchronous motors, and they run those when the power is cheap, but also when they need to correct power factor, because they get a special bonus for correcting power factor. And we also have capacitor banks that we switch in. So when we looked at electrical power, we saw that there were capacitor banks, and those will correct lagging power factor by adding leading power factor, and then those cancel each other out. If there's enough leading power factor from the capacitors, then you'll be in good shape. So that's it. Electrical power and three-phase transformer configurations.